Okay, good afternoon, everyone. So last time we went through the first part of the PCA notes where we talked about what is PCA and we derived it. And basically, let's summarize that now. So PCA is applied to a data set of features only. We don't generally talk about labels. We just have some features. For example, vectors x1 through xn. And as always, these are d-dimensional vectors. And our goal in PCA is to compress them to a smaller dimension, which we call capital R. So for example, if we have vectors or data points that lie in 3D, those are these points in 3D, we might want to compress them down so that they live in a plane. And our goal in compressing is to minimize the RSS of the error. So if we have the plane oriented as it is here, and this is a data point, then this would be the representation of PCA, and the error would be the length of that line, and the sum squared of all these errors is the thing that PCA tries to minimize. So that would be the example when we compress from 3 dimensions down to 2. And over here we have an example where we compress the same data from 3 dimensions down to 1. And so a one-dimensional hyperplane is just a line. And so we're saying what's the best line approximation of our data set. In other words, the one that minimizes the errors when all these points are projected onto that line. And that would be this line. So that's what PCA tries to do. It tries to find a linear representation of the data, meaning something that lies in a plane or a line or some sort of hyperplane of dimension R with lowest RSS. So that's the goal. And then what we found is the solution is we compute, well, first of all, we make sure that our x's don't have any mean in it, so we remove the mean as we do with standardization. Then we compute this covariance matrix Q. Then we look at the eigen decomposition of Q. In particular, we look at the eigenvectors, the R eigenvectors associated with the R largest eigenvalues. Those are the principal ones. And we stack those eigenvectors as the columns of a matrix V capital R. And finally, we have the projection operation. This is the projection operation. So if you want to compress xi, you multiply it by this wide matrix to give you your representation z hat I. So this would be an R-dimensional representation. This is a D-dimensional one. And if you want to understand, so this z hat I, for example, would be the pair of coordinates that tells you where you are on the plane, or would be the single coordinate that tells you where you are along this line. Now, if you want to understand where a point on this line lives in 3-dimensional space, you have to go back up to 3-dimensional space, and that's what this equation does. Basically, this is the 3-dimensional version of that reduced representation, and the goal is that it's not so different from the original data. Of course, whether this is approximately equal to it or not depends on how aggressive you are in compressing and how compressible the data set is. But that's the overall idea. So good time to pause and ask, are there any questions? Is it making sense? Yeah. No questions at all? Everything's good? Okay, so what we'll do today is we'll talk about how to compute this eigenvector decomposition efficiently, and we're going to show an example of compressing face images, and we'll talk about a few other considerations, why this could fail for classification, and some other nonlinear dimensionality approaches that are useful for visualization. Another thing we talked about at the very end on Friday was a way to measure or to quantify the performance of PCA as a function of the rank. so that we could have a way of choosing the rank. And we came up with this proportion of variance, which is a lot like R squared in linear regression. This is something that the ideal value would be 1. That's when the RSS is 0. So the higher this is, the better. And basically, it ends up being the ratio of the sum of the eigenvalues that we are in the dimensions we're approximating versus the sum of all eigenvalues. Okay, so that's what we did last time. And so now let's talk about how we compute this. So how many of you guys have heard of the singular value decomposition, SVD? Okay, this is a super useful decomposition for many things. Sometimes it can save you a lot of computation. Other times it can help you do a proof or just figure out, like, should I expect this property of matrix algebra or not? One of the really nice things about the SVD is, unlike many other matrix decompositions in linear algebra, this one works with any matrix whatsoever. It does not have to be a square matrix. It doesn't have to be full rank. It works always. So you can always take an SVD. Okay, so there's 2 flavors of it. There's the standard one and what I call the economy one. It's called that in MATLAB too. So let's talk about the standard one first. So the main decomposition is this equation here. It says that any matrix X can be written as the product of a square orthogonal matrix U, and then a diagonal matrix S that has the same shape as X, and then a square matrix V transpose. So let me show you a couple pictures of how this could turn out. So for example, if X was a tall matrix, and you're doing this, then the shape of the SVD, you'd have a big square matrix equal to the number of rows in X, and then you'd have an S matrix that has the same size as X, and then you have a V matrix, or V transpose, that has the same number of columns as X. And remember that this is diagonal, meaning it has some non-zero coefficients here, but everywhere else is zeros. So that's one way it can turn out if you had a tall matrix. Now, if you have a wide matrix, then you would have square U. S has the same dimensions as X, and you would now have a big square V. And again, S is diagonal. Okay, now this S can have zero-valued elements along the diagonal. So the diagonal matrix is guaranteed to be non-negative, and it's sorted from big to small. But you can have zeros in there. So there can be some zero-valued elements at the tail of this. And then these, the U matrix is orthogonal, similar to the, same with the V, similar to what we saw in the eigenvalue decomposition of a symmetric matrix. Okay, so this is the standard SVD. Another way that you can think about this is if you think about X as an operator, something you apply, an operation you apply to a vector. This says that you can think of that operation in 3 stages. A rotation, because that's what a unitary matrix does. It never changes the length of a vector, it just rotates it in d-dimensional space. Followed by a scaling of the rotated coefficients. That's what a diagonal matrix does. It just scales coefficients individually without mixing them together. Followed by another rotation. So any matrix multiply you can think of as rotate, scale, and another rotation. So that's kind of a useful interpretation of what this says. Okay, good time to pause. Any questions on this SVD? Okay, so often when you apply it, you can use these identities to simplify things that show up. Yeah, okay. So now there's another version, the economy SVD. And the economy SVD recognizes that all these zeros here, so this is like all these zeros are going to kill whatever is down here in this V transpose matrix. So in other words, the elements in that bottom half of the V transpose matrix or the right half of the V matrix are kind of useless. They're never involved in this decomposition. Same thing over here. So all of these are going to be multiplied by these zeros, and so these are kind of useless. So computationally, you might say, well, why would I bother computing all those columns if I'm never actually going to use them? And in fact, it's a little bit more than that. If you have a bunch of zeros here, then maybe a whole bunch of these will never be used, and a bunch of these will never be used simultaneously because they're all going to be multiplied by all those zeros. So then you would then say, I should just compute the columns here and the rows here that correspond to the non-zero singular values, the non-zero S's. And that's what the economy SVD does. So in the economy SVD, you might have something, picture like this. This would be a tall matrix. This is a little diagonal matrix that's guaranteed to have positive elements, no zeros on the diagonal. And then this one, this V transpose has to match the number of columns in X. So this is what you have with the economy SVD. You only compute the entries in the U and V matrices that are actually involved in the decomposition. And the nice thing about this S is it's invertible. It's square. The diagonal elements are never zero. Whereas this S is, well, first of all, it's not even square, but also it has possibly some zeros on it. So that's the advantage of this one. Now, on the other hand, you know that the columns in U, that we're actually calling this UR now. R is denoting the rank of X, or the number of non-zero singular values. So this UR has columns that are orthogonal to each other, but you don't have this other property. The rows are definitely not orthogonal to each other. And the same thing with V. V has columns orthogonal to each other, but not rows. So this is super convenient. You lose some of that convenience here, whereas this S is much more convenient here, but not as convenient up here. So the version that you use sort of depends on what you're trying to do, either in a proof or in your understanding or computationally. So those are the two forms of the SVD. Right. Any questions? Okay, so we're going to use the SVD for PCA. And I'll first try to convince you that the SVD is actually very similar to the eigenvalue decomposition. Let me be a little bit clear by adding some bars to these V's here so as not to be confusing. So I'm going to put bars on this V that is used in the top half of the slide. Okay, so even though when we talked about PCA and the eigenvalue decomposition before, we used V alone, I'm just going to rename it V bar to not confuse it with the V down here that we use for the SVD. Okay, so this is what we saw for the eigenvalue decomposition of the covariance matrix. And we know that this V bar is an orthogonal matrix, so it satisfies this. And we know that lambda is a diagonal matrix. We also know that this is positive semi-definite, which means that this lambda can never have any negative elements. And we said without loss of generality, we've sorted them from big to small. So this is what we have for PCA and the eigenvalue decomposition. So now let's think back to SVD. And we have for SVD, we have this equation, and we have our definition of the covariance matrix. So what we can do is we can just plug this into X and X transpose, and we get this expression here. And now we see that because we're using the full SVD, so this U is square orthogonal, so that cancels and becomes identity, at which point we get this. And now S might be a tall matrix. Is that true? No, S is going to be square. No, actually, sorry. S is probably, in most machine learning applications, S is going to be tall because we tend to have more samples than features. Not always, but usually. In any case, this S transpose S here will be square, and it will be diagonal. And when you look at its diagonal elements, this is what you see. So now we have these two different versions of Q. We have Q above, and we have this Q below. And when you step back and look at them, you realize they're essentially the same. So in both cases, we have orthogonal, positive diagonal, or non-negative diagonal times orthogonal transpose. We have that in both cases. And we see basically that means that the eigenvalue V bar is the same as the singular value V. And the relationship between the eigenvalues and the singular values is basically just the jth eigenvalue is the squared jth singular value divided by n. So that means that I can compute an SVD of x, and from that I can figure out the eigenvalue decomposition, or PCA. I never actually need to form this matrix here. And this matrix for large data sets can be very computationally intense to compute this. It can be more work to compute this than the SVD. And so that's the objective in never needing to compute Q directly. You start with X, you do the SVD on X, and then you never have to compute Q. But you get the eigenvalue decomposition by looking at the largest V columns and the largest few eigenvalues if you need them. Okay, so that's how we would approach it with the standard SVD. Any questions on that? Is that making sense? Okay, so basically it's like we're doing this, but we're just avoiding ever computing this X transpose X. We're directly getting what we need from the SVD. Okay, but now the SVD, at least the standard SVD, is still pretty wasteful because generally speaking, or often with PCA, we just want to compute a few of the a few principal eigenvectors, not all of them. And this actually would give us essentially all the eigenvectors. So we would really want to do the economy SVD. That's going to be more efficient. Okay, so the SVD, economy SVD computes only the top R singular vectors. R is the rank of our data matrix, which is the minimum of n, the number of samples, or d, the number of features. But what we really need is just the top R. And often, pretty much always, R is going to be, big R is going to be less than little r. So usually it's much less. So that suggests that we can compute the economy SVD, and even that will give us more of these than we want, more singular vectors, more singular values than we want. So that's what we tend to do in practice, compute the economy SVD. That gives us this matrix with R columns, little r columns, and we take the first big R columns of it, and that's all we need for PCA. Okay, so that's how we're going to compute it. And I'll show you guys a Python example in a moment. Okay, any questions? All right. So another thing we could do is, in the case that we do have some targets, I mean, this is not always the case, but maybe you do actually have some targets, and what you've done now is you've compressed your features down to some, lower dimensional version of them, and maybe now you want to try classification with those compressed features. So as we usually do, we want to standardize them because maybe we're using them with some technique that wants standardization. So if we want standardized features, then typically what we want to do is we want to compute the sample mean of all of our features. So that would be, we'll call that Z bar here. And we want that to be 0 for standardization. And we also want that the sample, so once this is true, let's say, we want that the sample variances are also 1 for every feature J. Okay, so these are the things we want, the 2 requirements. And another way to think about this guy is to think that that is the same as looking at the outer product of the Zi vectors and then looking at the diagonal of the outer product. So the diagonal of the outer product will contain these terms. And then this thing is the covariance matrix of Z, different from the covariance matrix of X over here. Different, but very similar. So what we want is we want that the diagonal of this covariance matrix is the vector of 1s. That's what happens when they're all normalized to unit energy. Okay, so this is what we want. Let's see what actually happens. So Z bar is going to be, remember, this is how we compute Zi. We take our raw features and we multiply them by VR transpose. And then here, to get Z bar, we just sum that thing across the data. So by linearity, we can move this averaging operation through the VR transpose, and now we're averaging the features. But we remember that actually we made sure earlier that these were already 0 mean, so this is just the 0 vector. And that means I have a matrix times a 0 vector, which is a 0 vector. So this wish is actually satisfied. We do have 0 mean compressed features. So that's great. We don't have to worry about that. Next question is this true, or if not, how do we get this to be true? So let's look at the covariance matrix of Q, of Z. So this is just the average outer product of Zi and itself. And we can again plug in this expression for Zi and put the sum in the middle. We get this. And then we recognize that what's on the inside here is the covariance matrix of the data, which we call Q. And this covariance matrix, Q, we know that its SVD, its full SVD looks like this: VR, S squared R, V transpose times 1 over n. And finally, we remember that this vector of the top R the matrix of top R eigenvectors contains exactly the first columns of this V little r matrix, and all the other columns are orthogonal. So when you do that matrix multiply, you get an identity matrix on the left and a 0 over here. So that means that when you do this whole operation, all it does is extract the first capital R elements in this diagonal matrix. In other words, you get this. So this is what we actually have. This is what we want. And now it's easy to see that all we have to do is scale the Z features by the inverse square root of these numbers. And then we get normalized or standardized features. So this is what we do. We take our Zi's, we multiply them by this diagonal matrix of scaling factors, and now we get our Z tilde i's, which are standardized. Okay, so this is essentially all we have to do. We have to do this scaling with the singular values, and now we have standardized zi coefficients, which we call zi tilde. So now we're able to use these for classification or whatever we want. Okay, any questions on this? Okay, so, all right, let's take a look at an example. So we're going to look at face data set. This is actually, by today's standards, these faces are pretty tiny. They're 50 by 37 pixels, so 1,850 pixels per face. It's from a data set made back in 2007. Just so you know, like modern face images can have like millions of pixels, so these are really tiny, but it's easy for us to do some experiments for the lecture and in the demo. And so we're going to basically try to compress them using PCA. So this data set is actually built into scikit-learn. And if you look at the data set, there's a total of 13,000 images. But some of the people in the data set don't have many data points. So we're going to look for, okay, so this data set is news stories from the 2000s. So you find characters like Donald Rumsfeld, Colin Powell, George Bush, Gerhard Schroeder, and a bunch of other people, but those other people don't have that many data points. So we're just going to use these. They all have greater than 70 faces for each of those. So from these 13,000 images, we're going to extract a subset of 1288 images. And there's actually 7 classes, not just these 4 people, but there's 7 people total. Okay, so when we look at the image size, 50 by 37, we have 1,288 samples. So actually, this is one of these weird cases where we actually have fewer samples than features. Right? In machine learning, usually it's the opposite. Usually have many more samples than features. Here we actually have fewer samples than features. And we do actually have class labels, so we can try that classification thing where we'll do PCA to reduce these to some lower dimensional representations, but then we'll still try to classify whose face it is from those reduced features. Okay, so that's the setup. So let's first try to figure out, okay, let's first do our data processing. So the first thing we do is we compute the mean for every, remember our X matrix has the data, always the data samples going down the rows. So for each of the columns, we compute the mean and we subtract it out of the X matrix. So now every column has 0 mean. Then we do NumPy, linalg, SVD, and we use full matrices equals false to do the economy version. And this gives us the U matrix, the S, a vector of the S singular values, and then the V transpose matrix. And when we look at the shape of the V transpose matrix, it matches what we expect for X, which is it has 1,288 rows, number of samples in the data set, and 1,850 pixels, which is the number of features per image. Now let's figure out what is a good number of principal components, in other words, R, capital R. So here we're printing the POV, the proportion of variance. To compute that, we basically square element-wise all our singular values, divide by the number of samples. That gives us our eigenvalues. And then we just use a cumulative sum for different values of R versus the total sum. That gives us our POV versus R. And remember, 1 is the maximum value. And you can see when R gets up to 400, it looks like we've extracted almost all the variance in the data. So it doesn't really seem like there's much point in using more than 400 principal components. We get really good compression with 400. And that's pretty significant. We're throwing away 2/3 of the data, right, to get this value of R. Okay, so that's just sort of a baseline. All right, any questions so far? Okay, so So let's look at the PCA approximations versus R. And this is for a couple faces. George W. Bush. So you can see in the titles, you see what value of R is chosen. So this is the full precision face, 1850 pixels, full resolution. This is if we use 300. That's a little bit less than what we saw on the previous page, right, for 400. But even at 300, it's not perfect, but it looks really good. You can notice that maybe like some creases in the face are gone a little bit, but overall, really good approximation. Of course, if you get more aggressive with your compression, as R goes down, you start to lose more and more details. At some point, it's really impossible to tell like whose face it is. You've compressed too much. But you can kind of see a trade-off here. More compression, more information is lost. But even with compression down to 3 numbers, you can get information as to like kind of which way are they facing, which way is the light coming from, and so on. So that's the approximations. That's the basically like the X hat. Let's look at the principal components, otherwise known as the eigenfaces. So this is the mean face. This is what we subtracted. So when making any of these, you have to start with the mean, and then you add onto it what you learned from the compression of the stuff that deviates from the mean. Okay, so this is the eigenvector corresponding to the strongest principal component. So we've, of course, reshaped this vector into something with the same size as the face, so we can view it. And then this is the second most important eigenvector, the third most important, the fourth most important, and so on. And it's interesting to see, how the images change. But keep in mind that each of these are orthogonal to all the other ones. That's what's special about PCA. So if you did an inner product or pointwise multiply of this times this and summed it, you would get 0. That's how PCA works. So these are basically the building blocks, the most 6 important building blocks of faces if you care about RSS. So, is this making sense? Helping to illustrate PCA? Okay, any questions? Okay. All right, so now we've done this decomposition, we've looked at it for various R's. We'll choose R equals 100, and we'll try to do some classification. So to do this, we'll split our data into test and train, and we will remove the mean on the training fold, compute the mean on the training fold, remove it, and then we'll do our SVD, again on the training data, again, economy SVD. We'll extract the top 100 principal components, and this is where we do, where we take our training data and we're multiplying by that V transpose matrix to get our compressed training features. And down here, we're doing our standardization. We're just dividing by the training singular values and the square root of the number of samples. So we get our standardized coefficients. Now that we have our standardized coefficients, we can train an SVM classifier. And as you remember, we have to do tuning over the regularization strength C and the radial basis function kernel with gamma. So we can make our parameter grids, and we can do grid search CV. And so we can do this in a matter of basically 3 lines, do fit according to our training data, training features and labels. And we find that we get about 85% classification, which is probably pretty decent, at least on the training data. And then we can repeat everything on the test data. Of course, we want to do our standardization, or subtract the mean of the training data, not the test data. And we want to scale according to the training statistics, not the test statistics. And on the test data, we get our classification accuracy of about 83%, which is not surprising that it's a little bit lower, but still pretty good. Okay, so that's just a demonstration of how we can go through those steps and do classification with these reduced dimensional features. So instead of using, what was it, like 1588, we're compressing by a pretty large factor, like a factor of 16 or so. Okay, any questions on what we've done here? Okay, so now what we've done here is actually a little bit weird. We shouldn't expect that classification is improved by doing PCA first. Usually things can get worse, and sometimes things can get a lot worse. So here we have sort of a worst case example, sort of contrived, but so let's look at this figure here. So we have 2-dimensional data, and this data is actually labeled. So class 1 has these data points, and class 2 has these data points. Okay, so let me ask someone. Is Josh Wolf here? No. Okay, what about John Saw? Okay, so where would the PCA hyperplane land on this picture?
I'm not entirely sure.
So let's remember what PCA is doing. So we're starting with 2-dimensional data. So if we're compressing, we must be compressing down to 1 dimension. So we're looking for a line. There's going to be a line somewhere on this graph. Another thing about subspaces is they must go through the origin. So the line must pass through the origin.
Oh, so would it be kind of that way then?
So this way or the other way?
The other way.
The other way, yes. Exactly. It's this way because we want to, again, think like PCA wants to minimize the sum squared errors to projections on this line. So like for this point, the error would be that big, and for this point, it'd be that big. And so if you think about, tilting this line different ways, you get some large errors as it's tilted. And this is actually kind of the worst case because these errors are super large, much larger than these. And RSS, because it's squared, it really cares about the biggest errors. It doesn't really care about little errors. It only mainly cares about big errors. So this is exactly where PCA would put the data set, and then all the samples would land right here, right? You would have all these samples right here. At that point, what happens to classification? Can you classify? No. You've lost everything useful to classification, right? So PCA is doing what you asked it to do. It's minimizing the variance in terms of its compression, but in doing so, it actually threw out the information that was most useful for classification. So that's where PCA can go wrong because it's not really designed to do some downstream processing that needs information that is different than just like the variance or cares, some downstream processing that is somehow not related to mean squared error. On the other hand, there is this thing called LDA, linear discriminant analysis. It's kind of an old famous technique. And that would say, I want to compress down to one line for this data set, but I want to make sure that I'm compressing in the best way for classification. You would actually come up with this line. And as a result, when you look at the distribution of the training labels along that line, you would see that all the 2s are here, all the 1s are here, linearly separable. It would work great for classification. Okay. So both techniques are linear, but they differ in the loss. PCA is looking at RSS, which doesn't really match a downstream task like classification, whereas LDA is really set up to do classification on these reduced dimensional features. Okay, so is that making sense? All right. Okay, so why use PCA? One of the biggest reasons that people use it is to visualize data. And it's not the only way to do this, but it's sort of one of the classical ways to do it. And the idea is that if you have data where you have 3 or more features, especially if you have many more than 3 features, we just can't visualize it as humans. But if you can somehow squeeze those features down to 2 dimensions, then we can visualize them very well. And so you sort of want to figure out what are the 2 dimensions that capture most of the energy or variance in the data, and that's what PCA does for you. So here we have 3-dimensional features. It's kind of hard to see how there's red, purple, green, blue. It's kind of hard to see the structure, but then we do PCA, and we get down to this plane, and you can see very clearly the structure in the data. And just an example, but so this is another big reason people use PCA, is visualization. So let's do something with a little bit more interesting data set. Let's look at MNIST. So with MNIST, as we know, there's, 384 features? There's way more features than we can visualize. So can we somehow get a sense for the data set if we squeeze everything down to 2 features with PCA? So here's principal component 1, principal component 2, like that. And again, when we do PCA, we don't use any knowledge of of labels. But what's done for this is, since we actually do know the labels, we can use the labels to plot where the different classes ended up in the PCA representation. So over here, these are class, digit 0. These are digit 1. Digit 2 is down here, and so on. And you do see that there is sort of a grouping. There's a clustering, but there's also a lot of overlap. So this is not ideal. Ideally, maybe we would get less overlap between these different digits, but we do see some structure. And it's also interesting to look at the principal components themselves. So this is the principal eigenvector. And gray is basically 0. Blue, I think, is positive, and red is negative. And when you look at this, it makes sense because as you go in the positive direction, that means make something more 0-like, and that's exactly where you find the zeros, is on the right side of the figure. And when you go this side, it means make this thing strong, the negatives, multiplying them by -1, and that's where you find the 1s. So you can kind of see the structure of this here. And then, of course, if all you had was one principal component, maybe you could kind of tell 0s and 1s apart, but it doesn't really help you to distinguish other digits. So when we look at the second principal component, we start to see a bunch of other interesting structures appear, things that might help you determine a 3 versus a 9 or a 7 and so on. And so that gives us this other dimension in the representation. And of course, these are just the first 2. There's the third, the fourth, and so on. But for visualization, then it becomes hard to visualize if I bring those in. In terms of data representation, there's a lot of useful information there if you care about classifying that's lost here. But this is what you get for visualization. So this is PCA with MNIST. Any questions on this? Okay. And now if you really want to visualize, it's best to use something maybe a little bit stronger than PCA, something that's nonlinear. And there's a bunch of classical methods. There's a kernel version of PCA, which kind of uses like RBF kernels combined with PCA. There's various other techniques, roughly 20 years old maybe. But the more contemporary methods work a lot better. Probably the most famous ones are TSNE, UMAP, and PACMAP. And so here's another picture of the compression of PCA. You can see a lot of overlap between the MNIST classes. But then when you go to TSNE and UMAP, you can see they actually do a great job of separating the classes. Now, I want to emphasize these methods knew nothing about the classes. They didn't know how many of them there were. They didn't know anything. But somehow they're able, just looking at the features alone, to notice that there's some sort of clustering. And then, to make the figure, that's when the knowledge of the labels was brought in just to color the different points in the scatter plot. Okay, so UMAP looks even better. Yes?
Why are if the purpose is the same, why are the graphs different between the three methods?
Well, PCA is just limited because it's linear. So, linear methods are just by nature simple. They're not very powerful. So this is, it's doing its best to come up with a two-dimensional representation of the data, and it's minimizing RSS subject to all possible linear compressions down to two features. These other methods are nonlinear. They have more sophisticated loss functions, so they can do more clever things. But they're different, between themselves. They're different. They work in different ways. There's also tuning parameters. So these figures look really nice, but often you have to tweak them. And as you tweak the parameters, then you might start to see this structure. And if things are not tweaked, TSNE might look like this or worse. So there's a little bit of maybe human guidance into tweaking these to try to expose the structure in your data set. But this can be useful if you're given a data set for which you don't know much about, and you're just wondering, is there much structure here? Can I somehow try to visualize the structure? You could try these approaches and try tweaking the parameters, and you might see these structures pop out, and that tells you, oh, that's really interesting. That must mean that all of these samples are similar to each other, all of those samples are similar to each other, and so on. And that's actually the task of clustering, which we're going to talk about in the next unit. But this is just, I wanted to let you know about these more advanced tools, not how they work, but just that they exist if you ever want to play with them. So, all right. So I think that's actually it for this unit. Any questions on anything PCA or other visualization techniques? Okay, great. So if not, then we'll start clustering on Wednesday. And I think we'll be able to get through clustering, and we'll still have several lectures left over. So I'm working on a unit on transformers, and I don't know if it's going to be about LLMs, but kind of transformers and some more modern techniques that people might be interested in. So, all right. See you guys on Wednesday.